Greetings to all and welcome to this lecture. We are in module 5, lecture number 3, that is introduction of MOS transistor. In previous lectures, we have found the 2-terminal and 3-terminal structures. We said that we do have a metal gate, an oxide layer and a substrate. This terminal we called it as gate, this terminal we called it as body. We started our analysis by analyzing these 2-terminal structure. Then we said that how we can connect this inversion layer through external world by adding a terminal which is C, and we saw the role of this voltage VCB. Then in this module we are going to start the 4-terminal structure, meaning we are also adding another terminal at this side, and we will see that what will happen when the inversion charge is connected between these two extra terminals. This is called 4-terminal MOS transistor. Here now we are defining another terminal, that is source and drain. So instead of C, we replace this terminal name by source and drain. We will see how we decide the region of operation of MOS transistor in this lecture. These are the learning outcome which helps you to understand the 4-terminal MOS transistor by extending our analysis on 3-terminal structure. This will also help you to define the different region of operation. So let us do a quick recap. In last lecture, we have found what is the VCB control in a 3-terminal structure. We mentioned that VCB control point of view does not mean that VCB is actually controlling your actual phenomena. It is just a viewpoint where we want to see what will happen if the 3rd terminal voltage, which is nothing but VCB, is increases or decreases. So this is N plus, and here you have depletion or inversion based on gate to body voltage. We found that when you increase VCB, ultimately the surface potential is increases and it will go to get saturated at value of psi SA. It means when you increase VCB, the surface potential or the channel, the inversion region of your channel is moved from strong to moderate to weak to depletion. So ultimately surface potential is linearly increases in strong inversion and ultimately switched your inversion from strong to depletion or weak inversion. We also mentioned that few of the voltage in terms of VQ, VW, VU, these are the boundaries between strong and moderate, moderate and weak and depletion region, and this is the value of VCB. We derived this equation such that what will be the value of VCB at which we will get this boundary. It means at this which the inversion transition take place from moderate to weak or weak to depletion or strong inversion to moderate inversion. So from this equation we can derive what is the function or what is the value of VCB. We got that VW is nothing but minus gamma divided by 2 plus gamma square by 4 plus VGB minus V flat band voltage into whole square minus 2 phi f. So this is the value of VCB which actually decides the boundary between moderate and weak inversion. We also saw that a pinch off voltage is defined as the value of VCB where VTB is equals to VGB and the inversion charge approaches 0. So let us start our analysis of 4-terminal MOS transistor. The MOS transistor is obtained by adding another terminal in the 3-terminal structure. As I mentioned, we will rename these terminals as source and drain. Similarly, following the same notations, instead of writing VCB, we are using another notation VSB. It means the voltage between source and body. Similarly, the voltage between drain and body is defined as VDB. Here what we are doing, we are actually applying a potential difference between these two terminals, which is actually contacted your inversion charge. If there will be a potential difference between these two, then there will be a flow of inversion charge which give rise to a current. Since the density of the carriers is actually controlled by the gate voltage, and hence this gate voltage can be used as a controlling knob. It means the moment you turn on the gate voltage, the inversion charge will be there. You can say the device is turned on, and the moment you turn off the gate voltage with some limits like above the threshold voltage or below the threshold voltage, then you can say there is no inversion charge and hence there is no current. So this voltage or the vertical field is used to turn on the device, whereas the horizontal field is used to cause the flow of electron from source end to drain end. In general, the basic theory of MOS transistor operation was developed in early 1960s, where extensive analysis was done based on diffusion current and substrate charge. But later in that decade, around 1970s, the attempts have been made to design the compact model for computer-aided design, which captures both drift and diffusion phenomena in the MOS transistor. So here we assume some approximations to go forward. First of all, we are assuming that the channel length is sufficiently large, and similarly the channel width. So this is a three-dimensional structure. This is the width dimension, right? So channel width and channel length is sufficiently large so that we can ignore the second order effect at this junction. Basically, if you see, this is p-type substrate and this is n plus region. So it's like this: you have n plus region, you have n plus region, and this is p-type substrate. If we see closely, here it is n plus p junction and here it is p plus n junction. So the depletion region will form like this. But the depletion region expansion will be there inside the n plus region also. For the sake of simplicity, until stated otherwise, we are not assuming the expansion of the depletion region inside the n plus region, and we will only assume this is nothing but one-sided junction. It means n plus p. So all the depletion region is expanded in the channel or the substrate. The second assumption we will make is that substrate is uniformly doped, and unless stated otherwise, this is nothing but p-type substrate. So the channel extension is considered from 0 to L, and again for simplicity we are mentioning 0 end is near to source and L is near to drain. So this point near to drain and this point is near to source, and we will analyze the MOS transistor in between these points. This figure, so if you see the earlier figure, is with respect to body terminal as reference. That is what we are applying VDB, VGB and VSB. But if we change our reference point to the source, then we can find the figure can be drawn like this, where source is a reference point. So we do have VGS where source is a reference point, VSB and VDS. We will analyze the viewpoint of VSB, VGS, VDS, and also when we take body as a reference. Let's get started. Let's analyze the MOS transistor considering a case when VSB is equals to VDB. Let's start the analysis by considering VSB is equals to VDB. Specifically, it should be clear here that the voltage VSB and VDB should be positive, because if this voltage will be negative, this region make this PN junction forward bias. If there will be a forward bias PN junction exists, then there will be a huge current flows between source and body like this, which is exponent current, because in forward bias we know the current can be given by as I naught e to the power of V by phi t minus 1, and we are not actually bothering about this current. We are interested in how to control the current or the charge flow between source and drain. So we will assume always VSB and VDB is positive, such that these junctions will be reverse bias. We will also assume the steady state values. It means after applying a DC voltage, the charge is at rest. The charges have reached the steady state value. Let us analyze the MOSFET by using a fluid dynamical analogy. So similar to MOSFET, we consider three reasons. One is source tank and drain tank, and this is channel. So let us analyze the MOSFET with fluid dynamic analogy. Here source and drain are represented by the water tanks, and channel is a hose or pipe in between these two tanks. Here the electrons are represented by the water molecules. Electric current is analogous to net water flow between source and drain. Source and drain are correspond to two large water tanks. We will ensure that even if the water flows, the water at the source and the drain tank will not be empty. In the sense, by some external means we will provide the water and maintain a constant level. This is analogous to the applied batteries or applied voltages VDB and VSP, which ensures that even if the current flows, this battery remains same. There is a piston connected in the channel. This piston, when we turn on the piston, it means this communication established between source tank and drain tank. So opening the piston means you are opening in the bottom side and VGS is increases. Similarly, increasing the VDS value and VGS value is in this direction or in the bottom of the tank. So what will happen? Let us consider when the piston is closed. If the piston is closed, there is no communication between source tank and drain tank, and hence there is no current. This is similar as in MOSFET. So you can consider this is N plus source, this is N plus drain, and you do have a gate voltage which is VGS. So I am measuring this voltage with respect to source terminal and drain terminal. So this VGS is with respect to source terminal, and you have a body. So the moment you turn on the device, meaning the moment you applied VGS, there will be a inversion charge. Similarly, when you open the piston, ultimately you are applying VGS and there will be a communication established. If VGS is less than VTH, or if VGS is very small, there is no inversion charge and there is no communication between source and drain sides. Now, when you applied a sufficient VGS or you open the piston, there is a communication between source tank and drain tank, but there is no flow of water because you are not applying VDS, meaning you are not lowering the level of water at the drain tank. This is analogous to drain water tank depth relative to the source representation, in the sense you need to lower the drain water level, right, from the source water level. It's similar as you are applying a VDS voltage with respect to source. So the moment you apply, there will be a flow of water starts. So water will start flow linearly and hence will get a linear current in between. Now what will happen if you increase VDS? If you increase VDS, then there will be a point comes into picture that the opening of this pipe is get limited by this edge, and hence whatever VDS you apply, the opening is fixed and hence you will get a constant flow. Let us analyze different reason of operation. As I mentioned, if the piston is closed, it means you are in cutoff region. There is no communication between source tank and drain tank, and hence the channel is not formed if you take an analogous to MOSFET. So if VGS is very small, piston is high, and there is no communication between source and drain tank, and hence there is no current. Now, how you form a channel? By increasing the VGS or lowering this piston, ultimately you made a communication between source and drain, which is similar to applying VGS into MOSFET. But until you apply VDS, there is no flow of the electron, because you are not actually creating a voltage difference between these 2 points. Now, what will happen when you apply a small VDS? Then level difference, there is a flow of water from source tank to drain tank, and hence the current lies linearly. But after a point, saturation region achieved, meaning even if you increase VDS, because of this edge constraint, the flow of water is limited, or the flow of water is constant. So the water entered slowly here, but it will go fastly enough to maintain the constant flow. That is what will get a saturation region of operation in MOSFET. So we'll again discuss about these characteristics when you plot the characteristic between drain current and drain to source voltage. We can further analyze the effect of gate voltage in different region of operation. For example, you applied VGS very low, in the sense the piston is closed. If the piston is closed, then also you can assume there are water vapors present in source tank. Similarly, there are water vapors in the drain tank. Even if VGS is low and you increase a bit level difference between source tank and drain tank, then the water vapors will go from this concentration to this concentration. This is similar as in the MOSFET. If VGS is low enough, or you are in depletion or weak inversion, and if you increase VDS, there is a very small flow of current, or there is a very small flow of charges. This is a weak inversion part. The moment you increase a bit value of VGS, then this flow is exponential, and hence we'll get that in weak inversion the current is exponentially dependent upon VGS by eta phi t or n phi t. We'll derive this equation in subsequent lectures. Now, what will happen if you increase VDS? That is what saturation. Even if you increase VDS beyond certain point, the flow is saturated, and hence you are in saturation of the MOSFET. So let's analyze the MOSFET technically, meaning using band diagram. For the sake of simplicity, let us consider VSB is 0. So again, you have N plus here, N plus here, you applied VDB and you applied VSB here. This is source, this is drain, and you have oxide and VGB applied in between. This is p-type substrate. For the sake of simplicity, we are assuming that VSB is equals to 0. This is like this. And we are assuming that VDB is equals to VSB. It means the level of the two water tank is what? Same. Now, when you apply VGB, what will happen? The inversion forms, like what we have discussed in two-terminal MOS. In the sense, if VGB is small, then what will happen? Then there is no inversion. If VGB is applied, then there is a sufficient amount of surface potential which causes the inversion. Let's analyze this using band diagram. So I am making a band diagram of N plus region, which is nothing but this is conduction band, this is Fermi level, intrinsic Fermi level and valence band. Now, as there is no current flowing into it, considering VDB is equals to VSB, the Fermi level is constant throughout, and this is Fermi level. So here again there is N plus region. This is N plus region is shown by like this. This is N plus region shown by this, and we do have a p-type substrate in between. P-type substrate means the valence band will come like this, and so you will get a band diagram like this. For the sake of simplicity, Here we have only plotted the conduction band energy with an understanding that conduction band, valence band and intrinsic Fermi levels follow the same trend. So this is conduction band energy, and line A represent when VGB is very small. In the sense, there is no formation of inversion region. In this scenario, if you see, there is a PN junction, and hence we'll get a built-in potential. That is what is a built-in potential Q into phi BI. Similar built-in potential will be here, Q into phi BI, where phi BI can be given as phi T log of Na Nd divided by Ni square. That's what we have discussed in PN junction. Now, what will happen when you increase VGB? If you increase VGB, considering VSB and VDB constant, the surface potential increases. The increase in surface potential causes to convert the channel into weak inversion or inversion. So surface potential increases. So this is the surface potential profile, and this is the potential energy profile. We know that the surface potential increases or decreases oppositively to the potential energy. So if the potential energy get lowered from A to B, the surface potential is increased from A dash to B dash, where A dash is 0, meaning the surface potential is almost 0 when your VGB is very small or nearly 0. Now what will happen if you increase VDS or VDB? If you increase VDB over VSB, then the bending will be lower. At the drain side, the bending will be lower because the increase in voltage reduces your potential energy, and this graph shows the potential energy of the electron. Similarly, when you increase the drain voltage, this side of the junction is got higher surface potential. That is what it can be represented by C dash. So the surface potential is increasing and the electronic potential or the potential energy is reduces. If there is a reduce in potential energy, the electrons will cross this barrier, comes under the vicinity in this part, and ultimately it will attracted by this electric field. This change in potential energy causes a horizontal field which is responsible for the current flow from source to drain. We can analyze, that's what we have already discussed, that the curve B shows the onset of inversion, where you applied this VGB, ultimately what will happen? There is a barrier lowering and the carrier go from source to channel. And the moment you increase VDS, it can be represented by curve C. By amount of QVDS, it will reduce, and hence there will be a flow from source to drain, which give rise to a current. For the sake of simplicity, in the subsequent lectures, we'll assume that in our MOSFET structure, the gate oxide is ideal. It means there is no leakage through this gate oxide unless stated otherwise, meaning the gate current is 0. We'll also assume that the formation of depletion region is ideal enough, and hence there is no base or body current. There is no body current, which means we'll assume IB is equals to 0 and IG is equals to 0 in our analysis. Further, if you see, we do have two components in the MOSFET. Further, if you see, we do have two component of electric field in the MOSFET. One is vertical, which is due to the applied VGB divided by the oxide thickness, and one is the applied VDB divided by the channel length. In this, we are considering the channel length is very large, and hence the electric field which is responsible, the electric field in the x direction is very small compared to the electric field in the y direction, because this is in the range of nanometers, 2 nanometers, 5 nanometers, and this is in micrometers, and hence electric field Ey is much larger than the electric field towards the X. This is called gradual channel approximation. So unless stated otherwise, we will follow the gradual channel approximation. It means we will assume that the horizontal field is lower enough compared to the vertical field. In general, we will also follow that the drain current is nothing but the current flows between source end and drain end, meaning we are not considering the other components of the current, and hence we will only consider ID is nothing but the current flows between drain and source, that is IDS. As we have seen in the previous graphs, here that the channel is here, the inversion charge is locally defined. It means it is a function of X. So we need to define locally the charge per unit area, that is Qi dash is equals to delta Qi divided by delta A. Here delta stands for we are actually defining the local charge per unit area. That is what we have already discussed in our previous lectures. Let us discuss the reason of operation of the transistors. Let me first explain the output characteristic of MOS transistor, which is plotted between IDS and VDB. Here VDB is the drain to body voltage, considering body as a reference. That is what VSB is coming here. If we plot like that, we will get different reason of operation. This is strong inversion, moderate inversion, and weak inversion, and these notations we have already discussed in our previous lectures. Importantly, here to mention how we decide the name of the region or name of the inversion region. So let me tell you, the name of the inversion region will be decided with the level of inversion at more heavily inverted channel. If the more heavily inverted channel end is strong inversion, we will say the MOSFET is in strong inversion. If the more heavily inverted channel end is moderate inversion, we will say it is in moderate inversion. To make you clear, let us consider that you are applying a VGB here and you are keeping VSB and VDB constant or equal. VSB equals to VDB. In that scenario, when you apply a small VGB, then there will be a depletion. After depletion, there is a few more carriers comes into picture, which is in weak inversion. So this end of the channel is in weak inversion, this end of the channel is in weak inversion. So we will say this is weak inversion reason of operation of the transistor. Now what will happen if you increase VGB? This end goes in a strong inversion, this end also goes in a strong inversion, because you kept VSB and VDB equal. So we will say we are in strong inversion. But now if you increase VDB, as we know from the 3-terminal structure, if you increase VDB, this end of the channel or the surface potential of the channel at drain side will get constant to psi SA, meaning the channel charge here will be decreasing, and hence if this is like the situation where the inversion charge will be more at the source side and less at the drain side. So we will see which region of the channel is inverted more. So this is in strong inversion, this is in weak inversion. We will say the region of operation is what? Strong inversion. Suppose if the VGB is such a way that this is in moderate inversion, this is in moderate inversion, and this is in weak inversion, we will say it is in moderate inversion. Likewise, we will follow this region of inversion throughout this course. This graph is nothing but the extension of previous graph, where we are taking source as a reference point. So if source is a reference point, ultimately you can consider VSB is equals to 0, because you are measuring the drain voltage with respect to source. If you see, the first part of this graph is linearly rises, and after a certain point it is getting saturated. So we will analyze how this is happening in subsequent lectures. The best method to see this graph is to plot in log scale. If we plot in log scale, we can clearly see the demarcation between weak inversion, moderate inversion and strong inversion, and these points we have already defined in previous lectures. So let me summarize. We have discussed the 4-terminal MOS transistor, which is formed by adding a second contact in the 3-terminal structure. We have also seen that how the charge will flow in the MOS transistor. We assumed that the channel length and the channel width is wide enough such that we can ignore or neglect the edge effects. We have also seen that near the N plus source and drain junction there is a transition between channel and the source or the drain. To avoid this transition, we assume that there is no expansion of the depletion region in N plus. Further, we assume that we are only interested in drain to source current and ignoring or considering the ideal effects like gate oxide is ideal and the depletion charge is ideal enough, and hence we considered gate current and body current to be 0. So we will stop here for today. Until then, take care.